Great. So, yeah, welcome everyone to another week's intercontinental seminars on gravity and cosmology. This week we have the chance to hear from Alfio Maurizio Bonanno. Alfio got his PhD in Catania back in 95. Then he moved to Strasbourg and then Alberta University. And he's been in Catania, permanent researcher since, I don't know, the early 2000s, I guess. And today he's going to talk about dynamical models of regular black holes and singularity resolution from effective quantum spacetimes. So thank you very much, Alfio. The floor is yours.
Thank you very much for the invitation to give this talk. It's very nice for me to have the possibility of presenting these recent results on this problem. And if you have any questions, please ask me. And okay, and may I ask you, Kostas, how much time do you have roughly?
Well, yeah, 45, 50 minutes. Yeah.
Okay, that's
plus or
makes
minus.
perfectly sense. So
yeah.
let's discuss what we all know. Let's say recap what we all know about the fate of a collapsing star. So in Newtonian theory, as everybody knows, the total energy of the system of a star which undergoes a gravitational collapse is given by these two expressions. So we have the mc squared mass minus the potential energy. And this simple formula tells us that eventually, for r small enough, the total energy will become negative. That means that pressure will not be able to halt the collapse, and the star will continue to radiate energy up to r equals 0. That means that we basically have an unlimited amount of gravitational energy which is produced during the collapse of a Newtonian star. And from this point of view, we can already rule out this possibility because it will be, let's say, against the fact that we exist and we are now listening to this talk. In a sense, that is an evidence, indirect evidence for the existence of a sort of a cosmic sensor. And therefore, we know that this type of picture is different in GR, because in Einstein theory, the total energy is always positive, but the evolution of the star becomes causally disconnected from our universe, provided an event horizon is formed. And therefore, people have tried to ask the question, under which condition do we form an event horizon? And there have been various types of conjectures. The most famous is the Israel and Thornhope conjecture, that basically states that an event horizon will form whenever matter distribution with stress energy tensor satisfies appropriate physical condition collapse until a trapped surface is formed. But then soon after, let's say, Roger Penrose came up with the famous singularity theorems, and other people have followed up after his seminal work, showing that a trapped surface, a singularity forms once a trapped surface is formed. A trapped surface, just to remind what we are talking about, is a closed-to space with the property that narrow beams of light orthogonal to it at any point of the surface decrease in area, at least initially, even when they propagate outward. And this picture was encoded in an important work by Oppenheimer and Snyder, which is represented in this Eddington Finkelstein diagram. So imagine we have, we consider a self-gravitating fluid with the classical energy momentum given by this expression, and we assume spherical symmetry. Then eventually what you can see, if we start from initial surface, at some point the surface of the star will cross the event horizon, and you will end up with a space-time singularity if you have no rotation into the system. And that's the classical picture. And an important explicit model of this picture can be obtained by using explicitly considering this type of coordinates, where if we write the metric in this form, where nu and psi are two generic functions, and the capital R is the radius of the two spheres, the Einstein equation break down in this rather simple expression. Epsilon is given by, the energy density is given by F prime over R square R prime, and P is given by F dot, and the Bianchi identities are basically amount to nu prime equals minus P prime of epsilon over rho. But the important point in this discussion is F, this capital F, is the so-called Misner-Sharp mass, which is given by this expression, which doesn't mean much if you look at that, but physically it is a measure of, let's say, of a quasi-local energy enclosed by an two-dimensional area of radius capital R. Remember that R is not a coordinate here, but it's the radius of the two sphere. And then in case of homogeneous dust, we can imagine actually that the collapse is the matter inside of our system is modeled by homogeneous dust. Therefore, we have a cosmological, let's say, homogeneous metric in the interior. Einstein equation have this simple form: epsilon is 3m over a cube, which is basically is the total density of the matter density of the system. P is 0, and the capital R must be related with the small a times small r, that is rather obvious, I would say. And the Misner-Sharp mass had this expression. And in this case, the space-time Penrose diagram for the evolution of our self-gravitating ball of dust is the following. Then the RB is the boundary of the surface, which we match with the Schwarzschild. We can analytically match the surface with the Schwarzschild exterior, and it turns out that when this boundary actually crosses this 2m surface, the star enters the event horizon, density will increase, and eventually what will happen is the following: when A will go to 0 and A will go to 0 at some finite time, the density will be infinite. The singularity will form. And in this case, we know that the condition for the formation of trapped surface is given by this expression, and in the case of this Oppenheimer-Snyder-Dutt model, the apparent horizon curve is given by what you have in this diagram. As soon as the trapped surface is formed, the evolution of the system is unavoidable, and you eventually hit the singularity at some finite time. And this T event horizon, T apparent horizon, is the evolution of apparent horizon that eventually will also hit the singularity at some radius, at some time. I mean, that is the classical things. The question is if we can let's say, have a model where the let's say quantum gravity of any other theory, we might not even think about other quantum gravity, but another gravity theory can avoid this, under which condition we can have something which is doesn't produce singularities. So let's consider a self-gravitating fluid of matter described in this case by a four-velocity field, and therefore the fluid again is characterized by an energy density epsilon, and also a rest mass density, which is m naught times n, where n is number of density of particles, and assume mass conservation. So we still insist that the matter is described by a fluid model. Okay. And now we can consider in this case that the first principle of thermodynamics can be written in this way. And for a non-dissipative fluid, where there is no production of entropy, the above relation basically tells us that d epsilon is p plus epsilon over rho in the rho. That's pretty standard. I haven't done anything really fancy or particularly new up to this point. Now, the things I would like to stress is that one can derive the energy momentum tensor for a perfect fluid. Of course, there is no unique way of doing that, but from the following Lagrangian, and one can the Lagrangian is L is minus epsilon, and one can compute the variation of the Lagrangian under variation of metric, assuming that the variation of n mu is 0, where n, we basically want there is no variation of baryon number flux. And under this condition, the n is given by equation number 3, and therefore equation number 2 can be related to the variation of the metric through equation number 4. Then once you have done that, you can actually have a Lagrangian, bright Lagrangian, and ask yourself what happens if you take the variation of this Lagrangian. Now, this is the new thing. Look at the question number 5. That was actually an old idea by Markov and Mukhanov in the 80s, which I resurrected for discussing regular black holes. Okay, let's see how equation 5 is written. So what I've done here, I have factored out the Newton constant from the sum of the geometric contribution and the matter part contribution in the Lagrangian, so that I have added a multiplicative coupling chi of epsilon in the whole thing, so that if chi is constant, we are back to classical GR. In other words, what I'm supposing here is that the coupling between the matter part and the gravitational part is not constant, but it depends on the energy density of the matter field. So if chi is constant and is precisely given by 8 pi g Newton, by taking the variation of equation number 5, as I've shown before, one obtains exactly all the well-known Einstein equation plus the energy momentum tensor. And that's, of course, what you expect. But if chi is a function of epsilon, we are led to another contribution. So in this case, the variation of square root of minus g chi epsilon is given by equation number 8. And in this case, the total variation of the action leads to a modified Einstein equation, which is which is equation number 9, where we have an effective energy momentum tensor characterized by an effective energy density epsilon tilde and p tilde. And you can see what is happening here. The effective energy momentum tensor is basically composed by two parts. One is the classical part that you have T mu nu times epsilon chi times epsilon, that we can assume that is an induced Newton constant, plus an induced cosmological constant. And that's the very nice, let's say, consequence of this thing is that T tilde mu nu is conserved because it has been derived from the variation of an action. So we don't break diffeomorphism invariant at any step. So we have an effective energy density epsilon tilde and an effective pressure given by these two expressions. If you want, if you see here equation number 10, epsilon key comma epsilon is the new effective, let's say, time-dependent, epsilon-dependent Newton constant, and we have a new effective cosmological constant. So, in other words, if I have now a theory where I predict how G depends on epsilon, I can plug this GS as a function of epsilon dependence in my equation and obtain a new modified dynamics for my gravitational collapse. And here is where quantum gravity enters into the game. Do we have such a theory? So of course there is it's not possible in this talk to talk in let's say in detail about asymptotic safety, which is what inspired me in doing this work. But I think it will be enough to show you this recent calculation I did myself with the group in Heidelberg, where in this plot what we did is to compute the scaling of the 3-point vertex graviton vertex in an asymptotically safe theory in order to explicitly compute the momentum dependence of Newton constant as a function of the external momenta. So in fact, what you have here, this capital Gn, is the dimensionless Newton constant in units of the Planck mass, okay? Computed at k equals 0, k is the normalization group scale, as a function of external momenta, which is P, which is really a physical momentum. And the dotted line is the same quantity, but instead computed at P equals 0 as a function of the normalization scale. So if you take this result as it is, what I am saying is that the Newton constant is expected to scale as a function of the external momenta in at least at Planckian energy. So it doesn't. So there is it's basically constant, and then it goes to 0 at very large energies, and very large means energy greater than the Planck energy. This P that you see here is the external momentum scale in units of the Planck mass. And this is interesting because it's the first calculation of the running of the through the propagator of the Newton constant as a function of the external momentum that you can find in the literature in an asymptotically safe theory of gravity. And I encourage you to read this paper to if you want to know more the details, but for our purposes, What matters is that this Newton constant is suppressed at very high energy. Basically, it must go to zero. So if this is true, we can imagine that we can cook up a very simple model of the running of G, looking at this result. No? We can imagine that G as a function of the energy density of the system goes to zero when the energy density is ultra-Planckian. So we can, the simplest, let's say, thing that you can imagine is a law of this type, which is also, in a sense, one can derive this from the beta function for G, assuming that K goes like, K squared goes like epsilon. And if you accept this, which is consistent with the presence of the Reuter fixed point at high energy, you find that chi and lambda are given by this expression, and you can solve your background equation and see what is the evolution of the system. And it turns out that in this case, the scale factor behaves in this way at very large times. Basically, the singularity is never reached at any finite time, and the space-time is geodesically complete. So what we try to do in a recent paper is to generalize the Oppenheimer-Snyder-Dutt model to this running, say, Newton constant model in the interior. And what we have done is to match the interior with the collapsing boundary with an exterior that has the form that you have here. So for the interior, we have used this Friedman-Robertson-Walker prescription. And for the exterior, a general spherically symmetric Schwarzschild type element where M of R is unknown. We wanted to determine this M by matching the interior part with the exterior part. And if you do so, in this case, the induced metric on the boundary becomes the following, that's using the Israel matching condition, and basically imposing that the jump of the second fundamental form across the boundary is zero, which is equivalent to say that the motion remains geodesic as you pass from the outside to the interior. And if you do so, you are left with the following form of the Misner-Sharp mass. So now you can see this is a very, let's say, counterintuitive, let's say, shape of the Misner-Sharp mass. You will not think that this form leads you to a regular black hole, but this is precisely the case, actually. If you see here, changing psi for m not equal 1 produce either a horizonless horizonless model or a black hole with an outer and inner horizon. And remember that because R is always greater or equal than RB times A of t, and A of t is always greater than 0, this is a regular geometry. The space-time is geodesically complete. And this is the content, the result of our recent paper. And so it is a completely different class of regular black hole, which comes from a Lagrangian. So let's say, I will not say for the first time, but it's very difficult to obtain regular black holes out of a Lagrangian description. And this is a model which has some, which might indicate that it's possible to produce this type of object. And the key element here was to have a Newton constant which was going to zero fast enough. Now one can say, okay, I don't like this asymptotically safe business because we don't have a definite proof that the Reuter fixed point exists. There is no independent evidence as we have in the lattice that this fixed point is there. It's very difficult to trust the computation of the effective Escher trigger because there is a still long way to go to show that asymptotically safe scenario is the correct one, although there are many promising elements. And so one can take let's say, a practical point of view. So let's see what Polyakov, I think this is a very inspiring, it was a very inspiring paper for me. And if you want to enter the subject of asymptotic safety, I encourage you to read this paper, which is in arXiv. It's by Sasha Polyakov, a few projects in string theory from 1992, and he has a very physical intuition why G should be running, because using the words of Polyakov, how to avoid the problem of renormalizability. And then they said, okay, the quantum convection diverges at very high energy. So because the energy of virtual passive or particle can be arbitrarily high, that's the meaning of being not renormalizable. But then he said the possible way out is to conjecture that the coupling constant in gravity is scale dependent and tends to zero at small distances. And then this anti-screening of the gravitational interaction is quite natural, since the larger is the cloud of virtual particles, being gravity always attractive, the stronger the gravitational force is. So this is precisely what one can expect from, let's say, vacuum polarization. Okay, if we believe if we trust the physical intuition of Polyakov. And so therefore I can say, okay, what happens if I play around with another functional form of G, and I assume that G goes to zero with the energy density with this different law, and then it turns out that I will not bother you with the details if you repeat the same thing, is that in this case A goes to zero as exponentially, or so a small a never goes to zero, and the external metric is given by this expression, which again has this very simple de Sitter core. Well, actually, before there was not the Sitter core, but the limit of f. This is the f function in the black hole metric has the Sitter core, and at very large distance you are back with the Schwarzschild solution, and as before, changing psi, you have that the behavior of the metric for different values of parameter is produce a regular black hole or a Rayuson-less object. So now we can ask the following question, and can we cook up, can we embed, let's say, this mechanism in a Ordesky theory, or in general, okay, Ordesky maybe not, but in a scalar theory? I mean, can we have a scalarization mechanism which produce a regular black hole and encodes the idea that the Newton constant, the effective Newton constant goes to zero at very large energy scale. So now we have to go out this fluid business and write, and let's consider a very general action, like you have seen in the equation 16. And X is given by this scalar field, and our metric signature is that. And now I know that most people in the audience know that the equation of motion is equation 17, and the effective energy momentum tensor is equation 18. Okay, and in this case we can also interpret this in a sense of a perfect fluid with pressure and velocity, but be careful here, because the perfect this density might not stay constant, might not be positive in this case. Okay, but let's do that. What we will say that P comma capital X is the new effective Newton constant, no? Of course, if we have a non-canonical kinetic terms into the theory, we have to be we have to be careful about potential instabilities. In particular, classical stability of the theory is guaranteed if the sound speed is always positive. Then there is also the issue about ghost, whether you might have quantum stability. And let's for the moment assume only the classical stability, okay? And then okay, let's now go on. Let's write a general static spherical symmetric metric as equation 20, when r of rho is the radius of the two spheres. And the Einstein equation in this case reads as in equation 21. And what I assume is that the Gn is a new effective coupling constant. Okay. Now, inspired by the previous discussion, we might assume that there is a regular self-regulatory mechanism where G goes to 0 when the field is very large. That's the simplest possibility, is equation 22, but I think one can experiment with that. And in this case, the non-canonic kinetic term will have this form, where V is some function of the potential, okay? So what we do now, we can try to do a reverse engineering to play another game. So I suppose I have this. I want to determine V as a function of phi so that I have a regular interior. That's something which was started by Bronnikov a few years ago, okay? So I use the same philosophy here. So from the TT and theta theta component of the Einstein equation, one can eliminate V and obtain an equation for A as a function of rho. And now I assume that there is a regular black hole. So I write the equation 25. That's an assumption. And so that, not 25, 24 can be integrated, and we get this A is a function of rho. So we have set the integration constant to 0 in order to recover asymptotic flatness. And so we can have, of course, horizons in this case, depending on the value of these of these values of this M and this B, this case, and for large values of rho, rho goes like R, and we are back to, as we know, to Schwarzschild solution. But now we have to solve the problem completely. So now we can still eliminate V of phi from the TT rho rho and theta theta component and obtain an equation for the scalar field in this case. And in this case, the evolution of phi as a function of rho is given by this expression. One might say, okay, but what happens with the evolution of V as a function of phi? So here we have the explicit solution for phi in this case, and everything is perfectly regular, and we can use this to now solve the equation and obtain V of phi. And V of phi is given by this expression, which doesn't look very nice, but we can rewrite this expression in terms of phi. And here you see that V as a function of phi is a very well defined potential. So are we happy with that? Well, to tell you the truth, not totally, because here I had to take this epsilon here, basically negative. So that means that in the end, what will happen is that the classical stability is satisfied, but for small value of phi, you might have ghost-like excitation. So the quantum thing it might not be totally safe. But on the other hand, this is, in a sense, is a spherically symmetric solution of our equation, which which comes from the progress of scalarization of our equation, which encodes the idea of a G Newton which is suppressed at very high energies, and it's a regular black hole. So I think at the moment, that is what I wanted to tell you. So to summarize the most, let's say, interesting points that I wanted to make, that the takeaway lesson is that we do have, at least if we use a matter field component, we do have a possibility of producing a regular black hole out of a dynamical collapse, provided G goes to 0 at high density. And this is a very robust finding. If G goes to 0 sufficiently fast, but it doesn't have to be a specific formula. You can change your formula. As long as G goes to 0, you will end up with a regular black hole without the need of any exotic matter, okay? And so, in principle, we have the possibility of simulating this kind of regular black holes with standard Lagrangian code, because everything is encoded in Lagrangian formalism. And that's, let's say, the most important message of my talk. The second thing is that it is a little bit harder to obtain something similar using a scalarization method or embedding this in an Ordetsky type of theory. And at the moment, I have only partially succeeded to do that, but it will be really interesting to hook up a consistent model. Well, this is satisfied. So I think I can stop at the moment here, and I have time for taking questions. Thank you.
Thank you very much, Alfio, for the very nice talk. Are there any questions? Yeah, if not, I would like to ask some. Oh, Yuta?
Yeah, sorry,
Yeah, sure.
I couldn't find the raise hand, but
Yeah, don't worry.
I mean, thank you very much for this really nice talk.
Thank you for listening, Jutta. Thank you very much.
And I was wondering, did you also look at the regular rotating black holes? Do you also have some that you obtained from then this Lagrangian formalism?
No, I haven't looked at that. It's certainly important things to look at that, but I don't know how to do it even in the Oppenheimer-Snyder case. So I'm not sure. Maybe one can do some perturbation analysis, but for the dynamical case, I think we don't even have the analogous of Oppenheimer-Schneider, that model in the rotating case. So that for sure, it's impossible for me to, I don't know how to proceed further. And for the static case, Well, that is certainly possible. It's just that I haven't done it. But in principle, one can try to look at that. Yes, for sure.
Yeah, because this would be really interesting, since we think most black
Oh,
holes
yes.
we have are rotating. So yeah, this is
What
would
one
like
can
to
do,
know.
yes, the best one can do is take this log form I have for the exterior, and okay, apply the Newman-Janis transformation.
Okay.
And
Yes, yes, yes.
then one can do, and one can try to match with the observation. That is possible. That's probably the easiest way of doing that. I haven't done that, but that should be rather straightforward.
Yes. Now I'm always looking for something that is derived from a theory and produces a regular rotating black hole. Because then one can also look at the perturbations.
Yeah, but even that's true. But even in GR, we don't have it, so we have to accept it. We don't have an analytical thing. I mean, analytically, we don't have it. But there is a possibility of using this model, which I just show you, and you do a Newman, let's say, Janis transformation. That is doable, and that's one can say, okay, I can look at astronomical, astrophysical implication of that. That's certainly possible. I will do that. I will play with this because it makes sense to do that.
Thank you very much.
Thank you.
Anyone else? Any other questions? Yeah, I wanted to ask some clarifications actually. Do you want to share the screen again, Alfio?
Yes.
So, yeah, I knew about the first part. I mean, the solutions with chi of epsilon. I didn't know about this generalization, let's say, to scale
No,
up.
that is something new that I wanted to exactly.
Yeah.
To talk also, to have your feeling about that.
No, it's definitely interesting. The thing is, I didn't quite understand how G Newton couples to. So can you go to the action to this P of pi x? I mean, yeah, 16. So here you have like R, that is a scalar, plus this P of phi, P of phi and x.
That's
and
general.
then
There is nothing. There is nothing. Basically, everything is general.
yeah, but this phi is not a matter field, right? It's gravitating. So
The phi is a scalar field that solves gravitating. It solves the equation 17. That's the
well, 17
Klein-Gordon.
is just the Klein-Gordon. Yes, exactly.
Exactly.
But then how does the G Newton comes into play? So
because
you just
if I write, because from equation 18, P comma X is G Newton.
Okay, so you interpret. Okay, so you interpret.
I
P
can
comma X
interpret
as,
at least that one possibility is this one, but that can be discussed. And yes, once I do that, now here I wrote. That is what I did.
Yeah. Okay. So yeah, I get it. And then this 20 in this like ansatz, let's say rho is your radial coordinate, right?
Rho, no, the radial coordinate is r of rho. R is the radius of the two spheres. Rho is another coordinate.
I see. Okay.
Otherwise, so if R equals rho, you are back to Schwarzschild.
Yes. Okay.
But that is more general. Otherwise, it's
Otherwise, regular.
Yeah, that's why. But then I can assume that I can take this equation 25 and obtain the
the regular solution. Yes.
the potential. So that's what I've done, but I haven't written anything on that. So if you are interested, we can discuss these things because it's at the moment is something which it's, let's say, work in progress, but I want to take the opportunity to talk, to present these things, because I know that you and maybe other people could have been interested in that.
Yeah, it's definitely interesting. And then the Klein-Gordon and all the rest of the metric equations are satisfied as well for this kind of solution.
Exactly. Yes.
Nice. Very good. Are there any other questions? Okay, let me stop the recording.